Here in our distance to school data set, we have our distance traveled. This is the exact same data that you saw here. It's just put in a different format, some long column. I can find things like the average, mean, median, mode. All of these are different means of measuring the central tendency. Our mean is just the sum of all the distances traveled divided by the number of units in there, which I don't know yet. So I'm going to just go back, accept the error, and I'm going to put in the count on my n, and I will count up all of the different points here by using the count function in Excel. And I find that I have 31 points, so my mean is that sum divided by my 31, or 8.7. That's one way of doing it. Of course, I could also let Excel simply do the math for me and say calculate the average. And that will return the arithmetic average. You see here the exact same answer of 8.7. Again, I'm getting rid of unnecessary decimal points. The median, the one in the middle, equals, I can search for it visually, or I can let Excel do the work. And I will just say, Excel, find the median for me. There we have it, 4.2. And the mode, well, I can again let Excel do the work. Find the answer that is given most frequently. For open-ended questions, you may get interesting answers for the mode, but in this data set, you got something relatively reasonable. Okay, going to format it all in the same way. There we have it. Our mean is 8.7, but our median is 4.2. Why is our mean greater than our median? Because we have skewed data, specifically positively skewed data. I'm going to flip back to when we plotted it. You see we have this long tail over here. It is positively skewed data. There's our mean, median, and mode. We also are looking at deviations. So let's calculate deviations. There we have it. I'm going to make this column a little bit wider. And our deviation is simply my point less my average. There it is, negative 5.7, because it is below my average. Putting the dollar sign in front of the average so I can copy and paste. There's all of my deviations. If you look at the sum down here, you'll see the sum of the deviations is 0, as I've said. Now going back to our formula, I'm going to make this a little smaller. Going back to our formula, we see that we take our sum of our deviations, I square them, and I divide by n less 1. So here we have it. I have my deviations. I need my deviations squared equals this times itself. That's one way to square it. I can also use the little hat raised to the power of 2. That will also work. Copy, paste. We have that. Sum of deviations squared equals the sum of my deviations squared. Always label what you're calculating so somebody else can see what you're doing. And sample standard deviation equals the SQRT, the square root, of my sum of my deviations squared, divided by, open parentheses, a number of data points less 1, close parentheses, and I'm good. So I find that the average distance traveled is 8.7 plus or minus 9. It's pretty broad standard deviation. Why is it this broad standard deviation? Let's go back to looking at the data. Well, no, it's flat over here, but spiked right there. So we have a very wide distribution of answers. And that width is shown here in our sample standard deviation. One would have called that leptocritic since it leapt up at a particular data point. Are there other ways we can calculate sample standard deviation? Yes. Equals standard STD EV point S for sample, P for population. If you leave it blank, it'll also just always assume it's the sample. So there's my sample standard deviation of my raw data. There we have it, calculated at 9 once again. See? Exact same data. And we had other ways of calculating sample standard deviations and means. I'm going to go back to showing that paper. We had the frequencies and probabilities when we had summarized data and our sample standard deviation listed here. You can also find these equations in your book on pages 36 through 39. Here's an example of how we can use that on the Irish Music tab, a worksheet of your workbook. They ask people a question: do you agree or strongly or disagree to the statement, Irish music is fun? And we got these responses. We now need to find what the average response is for this sample. We can, of course, plot this, as we often do. Insert, column, plot. There we have it. Select our data. Series name, Irish music's fun. Series values. That's the actual response frequencies that we're plotting. Okay. And the x-axis, I can choose both of this and get the 1 through 5 as well as the names. There we have it. Okay. Okay. Getting rid of the legend. And finally, formatting the data series to get rid of the plot, adding a border, solid line. There we have it. Okay. And adding an axis name as well. I'm going to type in the word. Oops. Easy. Layout, axis title, vertical, rotated, response frequency. Here, we no longer have just the raw data. We have data where we have the frequency of getting the response and the meaning of that response on a 1 to 5 scale. We need to find the weighted average. There is no way I can type in the word equals average and get an answer. Because the average on 1 to 5, the scale of answers, is always going to give me 3. And if I take the average of just the response, well, that's kind of meaningless. I mean, it just says how many people responded on average to a particular kind of possible response. You get 1.8. 1.8 is down here on my plot. It has nothing to do with my average. It's just plain silly. We have to find a weighted average, and we weight them by our frequencies as shown in our formula. So shown in our formula. So we take our frequency weighting equals this times the meaning or the value. So our frequency weight times the actual meaning of that. Copy, paste. So now you see it's done this each time. It's taking the frequency of responses. 5 people gave a response of 4 on a 1 to 5 scale. And our weighted and our number of responses equals the total sum of all the frequencies. So that's my n. And now I have my weighted average response equals the sum of my frequency weighted responses divided by my number of responses, or 4.2. Now 4.2 is about here, which kind of makes sense. On a 1 to 5 scale, most people said somewhere between 4 and 5, and so yes, the average response should say 4.2. Again, there's a quicker way. I took the product, I added it up, I divided by the sum of my frequencies. So I said I took the sum of my product of my frequency of getting a response, my weighting, my frequency weightings, and the meaning of those responses, the 1 to 5 scale, divided by the sum, the frequency of responses, and there's my 4.2. Excellent. Next, we need the sample standard deviation. Let's take a look at our formula once again. Our sample standard deviation, I can't use this formula, I can use that one. What I'm saying here, I take the sum of my deviations squared times the frequency divided by n less 1. All right. So let's go here. I have to take the deviations, I have to find the deviations, I have to square them, multiply them by the frequency, and add them all up. Quite a few steps. So I'm going to move this down a little bit and put in here deviations equals 1, that's the response encoding, plus the average response, 4.2. Here I'm going to copy it from column to column. I need to hold the average constant, so I'll put the $ there, copy and paste. So these are negative, this one's positive. My deviations squared. Very carefully, please notice I'm using the interpretations of my responses and my average, not this frequency. Here's my deviation squared equals that times itself, or equals that at 2, either way. Copy, paste, there we have it. And now I need to multiply the deviation squared times the frequency equals this times the frequency of getting that response of 0. Copy and paste. Finally, to get my sample standard deviation, I take the sum of all of this and divide by my number of units, number of responses, which is 9 plus 1. And I was supposed to take the square root of all of this. So I'm going to take the square root, SQRT. Close. There. Remove some unnecessary decimals. And there we have it. Our sample standard deviation is 0.7. So our average answer, our weighted average response is 4.2. And our sample standard deviation is 0.7. Took quite a few steps to get our sample standard deviation. There are other ways we can do this. I'm going to insert a new tab, move it, there we have it. Here's my Irish music. Show you another way of doing the same thing. Copy, paste. Let's also paste the column widths. Have it. Paste. Looks quite nice. We had, in that case, the full frequency of response. What if I just had probability? Equals this divided by the sum of all of the responses. Put it in percent format and add in my $ here and here. Copy, paste. Oops, I put it in front of the row number. That's wrong. It's supposed to be in front of the column. How did I know I was wrong? The last column said 100%, and that makes no sense. So there we go. Sometimes you look at your calculations and say, whoops, something went wrong. You need to fix that. What about just the probability of response? And I didn't have my actual frequencies. Well, we have the way of finding the weighted average. And that was just simply the sum, the products of my meaning of the response and the probability of getting an individual response. So I'm probability weighting these individual response values. What's wrong with my name? Oh, some product. No, products. Here we have it, 4.2, which is what we had before. I need to find my sample standard deviation. One thing I'll need to know in doing so is calculate the number of responses overall. And that is 9. If you're just given the probability, somebody has to tell you the number of responses is 9. If you don't know the n, you're going to be guessing. So to find our sample standard deviation, let's look at our formula again. We need to find the sum of our deviations squared times the probability multiplied by n over n minus 1. So I need the deviations squared times my probability equals, here's my response, possibility, there's my average. I'm going to need to square that at 2. Then I'm also going to need to multiply that by my probability of getting that response. I'm going to copy this from column to column. As I do so, I'm going to need to keep the average constant, which is the green cell. So I'm going to put the dollar sign there in front of the column letter. Copy and paste. Finally, we get the sample standard deviation. That would be equal to the square root of the sum of these deviations squared times the probability of getting each one times this n divided by n plus 1. Close parenthesis, close parenthesis, close parenthesis. And you have 0.7. Which is what we had here as well, 0.7. Now we said we did that n less 1, and it was an approximation. You can leave it out and approximate it. If you don't know the sample size, you have the approximate. Standard deviation. You're going to have to just leave out that n if you don't know the sample size. So that'll just be the square root of the sum of these deviations squared times the probabilities. You'll see you'll get a slightly different number. Yes, that sounds fine. A 0.6. It's just slightly different. And the results, or the reason why this is different is that my n isn't exactly 9. Now notice if I increase my sample size, it said I got this exact same answer, but instead from 900 people, you're going to see my two sample standard deviations roughly equal. So that n over n minus 1 is completely accurate. If you leave it out, because sometimes you don't know the sample size, you'll get a good approximate standard deviation for the data you have.